Good morning, everybody. Hope you're all healthy and safe. So let's continue with our section on additional operational properties. So as I had mentioned, we will be discussing about the convolution theorem in this lecture. So let's move on to it. That is, what is convolution theorem? We are given two functions f and g, okay, so which are piecewise continuous on the interval 0 infinity, and they are of exponential order also. This is an extra property that we have seen apart from the definition of convolution of two functions. So the functions are piecewise continuous as well as of exponential order. Then the Laplace transform of f star of g, that is the Laplace transform of the convolution of these two functions, is nothing but Laplace transform of f of t into Laplace transform of g of t. Okay, so we know that Laplace transform is linear, that is the Laplace transform of f plus g is nothing but Laplace transform of f plus Laplace transform of g. But that does not mean that Laplace transform of f into g, that is a product of functions, need not be Laplace transform of the individual functions, product of individual functions. Okay, but this is true in case of the convolution. So instead of normal product, if you are taking the convolution of two functions, we get the result, that is the Laplace transform of f star g will be nothing but the Laplace transform of f of t into Laplace transform of g of t. Okay, so let's just see how this is proved. So it is simple, you don't have to worry much about it. So let's see. Now we need to determine what is the Laplace transform of f star g, right? So we know f of s. What is f of s? F of s is nothing but Laplace transform of f of t, which is equal to integral 0 to infinity e raised to minus st f of t dt, and g of s is the Laplace transform of g of t, which is equal to 0 to infinity e raised to minus st into g of t dt. Okay, so here now for the purpose of proof, to prove this, I am just going to replace this like two different variables instead of t itself. So f of s, what will be f of s into g of s? This will be nothing but integral 0 to infinity e raised to minus s. Instead of t, I am using tau for f, okay, into f of tau into, and 0 to infinity e raised to minus s, I am going to use beta, f of beta into d of beta. Okay, so this is 0 to infinity e raised to minus s into tau plus beta into f of tau into, oh, this is g, okay, sorry, not f, g of beta into d tau into d beta. Okay, now I'm going to take the d tau terms out, that is 0 to infinity f of tau into d tau into integral 0 to infinity e raised to minus s of tau plus beta into g of beta into d beta. Now let us keep tau fixed. Okay, keeping tau fixed, and let t is equal to tau plus beta. Okay, so what will our product be? That is f of s into g of s will be nothing but integral 0 to infinity. We are doing nothing with tau, f of tau into t tau, 0 to infinity e raised to minus s into tau plus beta is nothing but t now. and it will be g of, what will be the value? It was g of tau plus beta. No, it was g of beta, that would be t minus tau, right, into dt. Tau is fixed, so instead of derivative on both the sides, this will become constant, this will be treated as a constant, so this will become, derivative will become 0, and we will get dt is equal to d beta. So we have replaced it. Okay, now what I'm going to do is I'm going to take this 0 to infinity e raised to minus st into dt. Now this integration, exchange of the integration is possible because of the fact that they are of exponential order and are of piecewise continuous. So that is an important factor in the convolution theorem. So this is f of tau g of t minus tau into d tau, right? Also there is one thing left, that is the limiting value. The limiting value is when we are replacing t is equal to tau plus beta, when beta is 0, t becomes tau. Okay, don't forget to change the limits while we are changing while we are substituting the value. So this is like from 2. So now this is very familiar to us, that is nothing but this is 0 to infinity e raised to minus st into our function f star of g into dt, right? Okay, so this is nothing but Laplace transform of f star of g. I hope you're getting the concept. So when we took the product of f of s and g of s and made the substitution to t is equal to 2 plus beta, and using the formula of f star of g, we obtained that this is equal to integral 0 to infinity e raised to minus st into f star g, that is a convolution of f and g. This is the formula for convolution of the two function f and g, right? That into dt. So this is nothing but if we treat f star g as a single function in terms of t, okay, so this is nothing but the Laplace transform of f star of g. So we get L of f star g is nothing but capital F of s into g of s. That is what we had to prove, right? Okay, so this is the proof of the convolution theorem. Now let's just see a simple example, that is we are asked to evaluate the Laplace transform of integral 0 to t e raised to tau sine t minus tau d tau. So this is nothing but the Laplace transform of e raised to t star sine t, right? This is the formula of the convolution of these two functions. Now this is, we have done the same example just now in the previous in the previous section when we had done with the convolution of two functions. So let's see whether the answer is the same. So by the theorem, by convolution theorem, I can say this is nothing but L of e raised to t into Laplace transform of sine t, right? So what is this? This is equal to 1 by s minus 1 into 1 by s square plus 1. Okay, so we can verify whether these two answers are similar. Into s square plus 1. So when we had done in the previous example, we had not simplified it further. I have just left it out. You can just verify it whether it is same. Actually it is the same. So this is much more easier to evaluate the Laplace transform with the help of the convolution theorem, right? Because the Laplace transform of the convolution of two functions is actually the Laplace transform product of Laplace transform of the individual functions. So this is much more easier and a simple method. Now with this we shall with the help of, now usually to determine the initial value problem, we need both Laplace transform and the inverse Laplace transform. So in a similar manner, we have dealt with convolution theorem, that is the Laplace transform of f star of g is equal to f of s into g of s, where capital F of s is a Laplace transform of f and the capital G is the Laplace transform of g. So here also we have the inverse form of this particular theorem, that is the Laplace inverse of f of s into g of s is equal to f star g. So that is we will be just using this to solve the initial value problems. So we'll just see one example related to the same. Okay, that is how to find the inverse of the inverse Laplace transform of convolution functions. So we are asked to evaluate L inverse of 1 by s square plus k square whole square. Okay, this is like a general thing. So I am going to choose, so we don't know the normal inverse, we know what is 1 by s square plus k square, but the power of it is we are not familiar with it. So I am going to choose here f of s to be 1 by s square plus k square, and this is same as g of s. So that f of s, what is f of s into g of s? F of s into g of s will be nothing but 1 by s square plus k square whole square. So we'll get Laplace inverse of f of s into g of s, that is f star g. Okay, so if f of s is 1 by s square plus k square, what will be f of t? F of t is Laplace inverse of f of s, and that is nothing but the inverse of 1 by s square plus k square. So this is 1 by k into sine kt, right? This is the value, and this is same as g of t, right? Both are same. So we know we are asked to determine what is L inverse of f of s into g of s for the chosen f of s and g of s. We know that L inverse of f of s into g of s is nothing but f star g. So here we know what is f and g. So f star g will be equal to integral 0 to t. What is f? F of t will be 1 by k into sine k2 into 1 by k, g is sine k into t minus 2, using the formula of convolution of two functions. Taking k common, 1 by k square integral 0 to t sine k2 into sine of k into, so here we'll be using the trigonometric formula of sine A, sine B. Okay, using that we get f star g will be equal to L 1 by 2 is common, so I'm taking it out common, 0 to t cos of 2 tau minus t minus cos kt into d2. That is by using the formula sine A sine B is nothing but 1 by 2 cos A minus B minus cos A plus B. Okay, so here instead of A and B we replace A by k tau and B by k into t minus 2. So you get the following value. Okay, so we need to find the integral, that is 1 by 2k square into 1 by, with respect to 2, so this is 1 by 2k into sine k 2 tau minus t minus cos kt. This will be a constant because there is no term of tau in it, so this will be tau into cos kt. And applying the limits, that is from 0 to t. So this is equal to 1 by 2k square. So when I apply t, I will get this is equal to 1 by 2k into sine k 2t minus t, that is t minus t cos kt and minus of sine minus t, and this is 0, right? So what do we get? Because tau is 0. So simplifying this and reducing it into a simpler form, we get f star of g will be equal to sine kt minus kt into cos kt by 2k cube. Okay, so you can just this is, you can either leave it in that manner itself, or you can simplify it to find what is f star of g. So this is actually the L inverse of 1 by s square plus k square whole square. Okay, the Laplace inverse of 1 by s square plus k square whole square is nothing but sine kt minus kt into cos kt by 2k cube. Okay, so this was an example. Now what we are going to do is we will be dealing with more examples, so you don't need to worry about it. So just keep in keep in your mind basic formulas, basic transforms, that is Laplace transform of sine, cos, then their corresponding inverse also. Then none of this will be a bit, so tedious for you guys. You just have to work out the formula. So next is the concept of transform of an integral. Okay, so we have done the derivatives of transform, and here now we are going to introduce the transform of an integral. So this comes directly from the convolution theorem, that is, if we are supposing that the function g of t is 1. Okay, if g of t is considered 1, then L of g of t is nothing but 1 by s. That is a well-known formula. So when we apply convolution theorem, we have L of f star of 1 is nothing but L of f of t into L of 1, that is 1 by s, into f of s, that is f of s by 1 by s. Okay, or in other terms, if we apply the convolution formula, that is what will be convolution of f and 1, that is integral 0 to t f of 2 d tau. G is 1, so that is 1. So we get L of, this is what you have to keep in mind, that is the Laplace transform of the integral of this function. Laplace transform of integral 0 to t f of tau d tau is nothing but f of s divided by s. Okay, so from this we can see that what will be the Laplace transform. This is much more useful for us. Laplace transform of f of s, inverse Laplace transform of f of s by s, that will be nothing but integral 0 to t f of tau d tau. Okay, this is what which will be very much useful for us in terms of solving problems and all. So with the help of this, we can easily evaluate various functions, Laplace transform of various functions, so that you can just see how can we apply the transform. I mean, how are we going to apply this transform of an integral to determine the Laplace transform. So I'll just show few examples, like L inverse of, if you are asked to determine, usually this L inverse is applicable because we have to solve the initial value problem, right? So if you are asked to determine what is L inverse of, say, 1 by s into s square plus 1, what I'm going to do is I'm just going to write this as 1 divided by s square plus 1 whole by s, both are same. So this is actually of the form L inverse of f of s by s. So what is the value? That is nothing but integral 0 to t into f of 2. What is f of t? This is L inverse of f of s. Now what is f of s? 1 by s square plus 1. So that is nothing but sine, right? So here it is f of 2, so that is sine 2 d2. So what is the integral of sine? That is minus cos, varying from 0 to t, so that is minus cos t plus 1. See how easily we have got what is L inverse of 1 by s into s square plus 1. Here you can either use a convolution also, like treating f of s and g of s or not, that is what. So transform, this is very useful to determine the Laplace inverse of functions of the form f of s by s. Okay, so again we can just see one more, that is what is L inverse of, what will happen, 1 by, same thing, I'm just increasing the multiple of s, power of s. So this again I can write it as L inverse of, in the denominator I need only s, so I'll take 1 by 1 more s will come. Okay, so that is nothing but L inverse of f of s. Here f of s is where f of s is nothing but 1 by s into s square plus 1. So we need to determine what is f of t, right? So if f of s is this, then L inverse of f of s, that is f of t, equal to f of t is equal to the Laplace inverse of 1 by s into s square plus 1. So here just now we have seen what is L inverse of 1 by s into s square plus 1, that is 1 minus cos t, right? L inverse of 1 by s into s square plus 1 is nothing but 1 minus cos t. So that again we'll apply, so we'll get L inverse of 1 by s square into s square plus 1 will be nothing but integral 0 to t, f of t is 1 minus cos t, so 1 minus cos 2 into d2, that is nothing but 2 minus sine 2, varying from 0 to t, that is t minus sine t, and the rest is 0. So proceeding like this, we can find the Laplace transform, inverse Laplace transform, with the help of this convolution theorem. We are winding up our session of today, so thank you, stay safe and stay healthy.